Okay, so we've taken our data on both the resistor and the light bulb. So now you have to decide, how are you going to run your life? How are you going to run your classroom? What do you mean by that, Friendsley? Well, here's the deal. You've got data of voltage and current. You've got data of voltage and current. Are you going to plot voltage going up versus current going to the right? Or are you going to ask students to graph current going up and versus voltage to the right? You have to make a decision. All right, so what if you ask students to plot voltage versus current? Voltage goes up and current goes to the right. Then resistance is the slope of a V versus I graph, just straight up the slope. And the V versus I graph must be aligned through the origin to be considered ohmic. That's what it means. Ohmic means voltage and current are directly proportional. And directly proportional means a line through the origin. Got to be both, a line and through the origin. Can't be one or the other, got to be both. That's a direct proportion, and that is ohmic. Now, what if you ask your students to plot current versus voltage? Then the resistance is the reciprocal of the slope on a current versus voltage graph. Once again, the graph must be aligned through the origin in order for the resistor to be considered ohmic. So, why current versus voltage? Well, I like voltage versus current because the slope is just resistance. But the AP exam people who write Physics 2, they love current versus voltage. They love current versus voltage. They're gonna and so what I found is that it's about 9 times more likely for students to see or deal with current versus voltage. Current going up and voltage going to the right. Why is that, Friendsley? Because current is the dependent quantity in real life. It depends on the potential difference. Potential difference is chosen by the battery. It's not chosen by the resistor or anybody else. But the current depends on the potential difference. That's why a lot of people use, in fact, real electrical engineers are always doing current versus voltage. But that means that you need to prepare your students for seeing current versus voltage and taking the reciprocal to get resistance. All right, here's my data for the light bulb. I hope you can see this. As I added AA batteries, you can tell that my AA batteries were not very good. I mean, they're supposed to be 1.5 volts, and I'm not even getting 1.5, 3, 3.5, 4.5, 6, or whatever. I'm getting these dinky amounts, and I'm getting these currents off of the ammeter. When I plot them for the light bulb, you'll see that it's trying to be a line, but the line clearly misses the origin. In fact, you're supposed to get closer to a parabola shape for a light bulb. So why is it a parabola shape, Friendsley? Well, because I plotted voltage versus current. Voltage versus current. Because I plotted voltage versus current, the slope is just resistance. For a light bulb, the slope should increase as the voltage and current increase because the resistance of a light bulb becomes more and more as the light bulb gets hotter. That's a discussion you want to have with your students. That the temperature of a resistor, as the temperature increases, the resistivity and therefore the resistance of the resistor increases. You want to have that conversation with your P2 kids. Maybe not so much your P1 kids, but your P2. Here's the resistor, and you'll see very nice line through the origin. Look at that. Goes through the origin, the resistor is ohmic. All right, here's the last of our little discussion items together. Here's the last of them. Students need to be able to deal with ideal batteries that are not ideal. What is a non-ideal battery? Well, we model a non-ideal battery as an ideal battery with a little internal resistance in front or behind it. Now, does that mean that at the resistor factory or at the battery factory, the person who assembles the battery sticks a little resistor in the battery? No. The very same chemicals that create the EMF also have resistance. It's unavoidable. Some batteries are specially built to have very low internal resistance. Think car batteries. And some batteries are built with other ideas in mind. For example, watch batteries. They're very small, but they pack a punch. They're 3 volts. That's more voltage than a D cell. But they have a lot of internal resistance. That's the payoff. You have a lot of voltage in that little space for your watch battery. A lot of internal resistance is unavoidable. Students need to be able to model non-ideal batteries as an ideal battery, EMF, in series with a resistor. They need to be able to experimentally determine these things about a non-ideal battery. The battery's internal EMF, if it were a perfect battery, how many volts would it be? The battery's internal resistance, how many ohms are we pretending are in front of or behind the battery? Also the maximum current that the battery can deliver. If you take a battery and you connect it back to itself, if you take a battery and connect the battery back to itself, then the battery will deliver a maximum amount of current. It will not deliver an infinite current. In fact, the maximum amount of current that a battery can deliver is the battery's own EMF divided by its own resistance. Because if you tie a battery back to itself, the only voltage is the EMF and the only resistance is the internal resistor. So, I would encourage you to get one of these terrible, cheap 9-volt batteries from the Dollar Tree. I have no reason to believe that they would go out of their way to make this internal resistance small, so it's probably going to be a decent internal resistance. I'm expecting about 3 ohms. Okay, several low-value resistors. I would get 10 to 30 ohm resistors at least. Each lab setup probably needs 5. Okay, each lab setup could do with 5. Or get an adjustable resistor that can give a resistance between 5 and 30 ohms. Do you need to know the value of the resistor? Not at all. You will not measure the resistance in this lab. So you can just get a resistor, potentiometer or variable resistor that can go between 5 and 30 ohms. That's all you need to do. You don't even need to know the number of ohms on each trial. Voltmeter and ammeter, you need them both, or 2 multimeters, just like the non-ideal resistors. We're going to measure voltage and current for several trials. 5 trials get different voltages and currents. And then however many alligator clips you need to make the circuit. We need an ammeter that can measure probably up to 2 amps. Just warning. The voltmeter needs to be able to measure voltages up to about 10 volts because it's a 9-volt battery. So what are you going to do? You're going to connect the battery, a resistor, and an ammeter in series. Okay, just like we did with the other lab, battery, resistor, ammeter in series. Then you're going to connect the voltmeter in parallel to the battery. We're measuring the voltage on the battery now, not on the resistors. That's a key difference between this and the non-ideal resistors lab. On each trial, we're going to measure the current and voltage for the battery. Then we're going to use the resistors to make different amounts of current. Are you going to start with a weak resistor and then do more and more resistors in series? Or are you going to start with a high resistance, but then lessen the resistance by adding more and more resistors in parallel? That would be a good conversation to have with your students. Hey, we're using 5 ohm resistors. 5 is too low. So then we're going to put more and more resistors in series to make the resistance higher and higher. Or we're going to start with 50 ohm resistors. That's too high for this particular lab. So we're going to put more and more 50 ohm resistors in parallel so that the resistance is less and less. On each trial, connect a new resistor. Okay, have that conversation I just said with your students about how you connect resistors in series or parallel to make more or less resistance. Again, okay, so now let's actually do the lab. So we're not going to plot data, we're actually going to do the lab now. So let's do our lab.